Last time we did basically an exercise. We solved for the Riemann tensor components for a specific type of symmetry. Now I know it was very fast, we did a lot of stuff. What I'm going to do today is different, but it's basically a review. We're going to do the same kinds of calculations for a different exercise. If we have time, we'll go over the previous class's stuff, which is basically the same exercise, just with slightly different numbers, so to speak. Okay? And if we have time at the end, I'll just give you like a little outline of how you would do it in general for any case. But again, the best way to do it is through an exercise. First, let's start with this page. Okay? This is the kind of thing that you'll be doing throughout these kinds of calculations. All right. For example, for the Friedmann Robertson Walker, let's take the simple case we have flat 3 space and only R of t in the front. Okay? Right, if we have this metric, minus dt squared plus r, let's say square of t, times flat space, flat 3 space. All right? Now, if you use this formula, you'll find, for example, on the Riemann tensor components for the Friedmann Robertson Walker, it comes out almost by inspection. There's almost no calculation to do. Minus dt squared plus r, let's say square of t, times flat space, flat 3 space. All right? So I wrote down in the second line on the right-hand side, I wrote the little g's. Satisfy yourself that those are in fact the little g's. The second line says gt is plus 1, a to t is minus 1, gr is equal to that. Okay, you see those little g's? Do they make sense to you? Right? gt is just plus 1 is a positive square root of the thing in front of dt squared, which is just 1. What is GRR for the flat Friedmann Robertson Walker? Right, if we have this metric, minus dt squared plus r, let's say square of t, times flat space, flat 3 space. All right? This is dr squared plus whatever. This part of the GRR is just 1. The other part is r squared. The square root of that is r. The square root of the g. So all we have is just r. A to t carries a signature as minus 1. gr is the square root of the thing in front of the dr squared. That's simply r, which is r of t. What are the Riemann tensor components? Plug that into the formula right above it. Okay? Now, let's look at, I wrote over here, r, Riemann TA, TA. A could be r theta or phi. So it'll be tr, tr, t theta, or t phi, t phi. Okay, A can take those 3 values. And it has the same situation, right? It only has this one term. Why? What happens to these 3 terms? If we're talking about a mixture of t, let's say t theta, or t phi, or tr, tr, which term in here can you immediately tell me is going to vanish? Let's say if we're doing RT. All right, if you have a TR, you're going to have the GT with respect to R derivative and the GR with respect to T. Now, what's the GT with respect to R? GT is just 1. So no derivative with respect to that term. GR with respect to T will have a derivative because you have the R of T in there. What about common intermediary coordinates? What common intermediary coordinates are there for T and R? Nothing, because T itself has no derivative, so right away it falls apart. So there's only one term, the R with respect to T. So you're going to have the GR with respect to T and the GT with respect to R. GTT is just 1. So you have no GTT with respect to R. So you have only GRR with respect to T. GRR, right, if it's flat, then dr squared just has 1 as the spatial thing, plus the R of T, right? For example, if we're taking, let's say, the TR, right, you're summing over, if this is, let's say, TR, so all of this is TR, 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 these are the ones that are not TR, like theta phi.
And you sum.
Yeah, and you're summing. So these derivatives are only for coordinates where both the A and the B metric coefficients have derivatives for that coordinate. So you're going to have here derivative of R with respect to T. Here you're going to have the derivative of the dt component, which is 0, the GTT component with respect to R. So you just have this piece. So it's the r with respect to t divided by the g of t, which is just 1. So you just have r dot and another dot. You get r double dot. And you just do the calculation. All of these things that you've seen in the Friedmann equation, right? The r dots and the r dot squares and the r double dot, come right out of this. All right. Now I'll show you the formula, and within 2 minutes, by inspection, you'll be able to derive the Einstein equation, or at least the left-hand side of the Einstein equation, which is the Ricci, because it's on my website. They can look at the formula. Just almost by inspection, after you get used to it, you start seeing how the terms come out, and you can almost write it down just straight out without all these crazy long calculations. All right? And that will be for any diagonal metric. For example, the Schwarzschild metric. And the Riemann tensor component formula itself is also simple. I'll show it to you. And then maybe as a part of an exercise, you can do some calculations. For example, Friedmann Robertson Walker. All right. Now, there's also a paper that I gave you, which...
So this will be your problem.
This will be, well, there's several, I can give several, I don't know what, I'll have to speak to you with. One problem, okay. I gave you also
and it will be 10% of...
whatever, you'll figure it out. And there's
you can give them also your web page, no? That they can look at it.
Okay. If you just put my name, Avi Rabinowitz, then you'll come up with my website right away. Just find that. Okay, so you can do this like for Friedmann Robertson Walker and Schwarzschild. It comes out very, very... Because it's on my website, they can look at the formula. GT is just plus 1 is a positive square root of the thing in front of dt squared, which is just 1. A to t carries the signature as -1. GR is the square root of the thing in front of the dr squared. That's simply r, which is r of t over the square root and so on. What is the GR? What is GR? It has two pieces, right? It has the r of t, and it has the function of r part. We take the derivative with respect to time. The function of r part is not going to do anything. We're just going to have a derivative of the r, which is going to be what? R dot. So the derivative of that thing is just going to be r dot times the r part of the function. All right? Now, if we divide by the g, any of the other spatial g's, if we divide by, let's say, gr, what are we going to get? The spatial part will cancel out, and you'll just have r dot over r. Again, if you take gr, be r times its spatial thing, take the derivative of that with respect to time, you'll just have r dot times the spatial thing. Divide it by itself before it was taken a derivative, you'll have just the r with the spatial part. The spatial part will remain the same, they cancel out. You'll end up with r derivative over r. Okay? If you took a second derivative, you'll get an r double dot over r. So the terms that we're going to see when you do this calculation, okay, are going to be something like r dot, and then if you have products of these gammas, what are you going to see? You're going to see an r dot times an r dot. You have r dot squared, again, over r squared. Okay, look on page 8. Okay, where I wrote summary. It's a homogeneous, constant curvature, everything is the same. So therefore, the TR and the T theta and the T phi all turn out to be the same, and those turn out to be r double dot over r. The theta r, the theta phi, and the phi r all turn out to be the same, and they turn out to have these two pieces in there. What are those two pieces? The k comes from the fact that it's a constant curvature. The r dot square comes from that, like the gammas with the r, and the 1 over r square also from the same terms. If you do the calculation, you'll see exactly where each of these terms comes from. So basically, we have two types of term, an r dot double dot over r, and a k minus r dot square over r squared. I'm going to skip over the whole calculation. You can do it at home. It's an extremely important calculation. This will basically give you the Einstein equation solution for cosmology. The only thing to speak of in these pages that I didn't tell you about in class again is I compared the solutions for the metric that we gave, the minus dt squared plus r squared over 1 plus kr squared, etc., to what would happen if we didn't have the r of t in it, or what would happen if we didn't have the minus dt squared in it. We only had three-dimensional space and so on, so that you can see where each factor climbs into the final result. Why it's so crucial to have the minus dt squared, why it's so crucial to have the r squared, and so on. All right? And then once you go through that, if you want to, it's really simple. It's probably do the whole thing in half an hour or something like that. What I do also in here is I compare to what would be the situation if you didn't have one of those terms. Let's say if you didn't have the r in there, the r of t, or if you didn't have the